has an antenna with a total noise temperature of 50K and the physical temperature of 300 Kelvin and an efficiency of 99%. Its transmission line has a physical temperature of 300 Kelvin and efficiency of 90%. The first three stages of receiver all have 80K noise temperature and 13 dB gain. The receiver noise temperature is, here receiver noise temperature is nothing but 80 plus 80 divided by 20 plus 80 divided by 20 square is equals to 84.2 Kelvin. Here this is gain is nothing but given in dB. So 13 is equals to 10 log G. So which is nothing but the G is approximately equals to 20. So C is correct. The system noise temperature at the antenna is, so system noise temperature is nothing but ambient temperature, antenna temperature, ambient temperature and efficiency of an antenna minus plus transmission line temperature 1 by ETL minus 1 plus 1 by ETL into temperature of the receiver. So if we substitute all the values we will get this as a 180 Kelvin. That is option B is correct. The angle modulated wave is given by Yc of t if the phase deviation of the angle modulated wave is, the maximum phase deviation is nothing but 50, that is this, the maximum value of this decides maximum phase deviation. So 10 plus 5 is the maximum phase deviation, that is 15. Option C is correct. The bandwidth occupied by the angle modulated signal is, see, omega I is nothing but omega C plus del F. So del F max is equals to omega I max minus omega C. So omega Fi, that is equals to 1 by 2 pi d of dt 2 pi fct plus 10 sine 2000 pi t plus 5 sine 4000 pi t. Now if we differentiate, we will get it as fc plus 20,000 pi plus 20,000 pi. So delta f max is nothing but 40,000 pi divided by 2 pi, which is 20k. So f max is nothing but 2k. So bandwidth is nothing but 2 into delta f plus fm, that is 44 kilohertz. That is option A is correct. Loop control system for regulating the generator terminal voltage E0, which is shown in the figure. The forward path gain is 200 and the feedback factor is this 0.1. The reference voltage for keeping E0 to 50 volts. E0 is nothing but G by 1 plus GH into ER. Here this is 250, G is 200 divided by 200 into 1 by 10. So 200 by 21. So this is ER. ER is equals to now 21 by 200 into 250, which is equals to 26.25 volts. That is option C is correct. Percentage E change in E0 is equals to, here percentage change is this one, 200 divided by 20 ER minus 200, this is 180 new one, ER divided by 200 by 20, this is 21 ER. So if we calculate this one, we will get it as into 100, 0.526%. That is option C is correct. Consider the following multiplexer where I0, I1, I2, I3 are data input lines given by selected by two address lines A1, A0 and EN is the enable input. For the multiplexer to do its function, first of all it has to be enabled. So if we write the truth table for that one, that is X, Y, Z, F, there are 8 combinations. So whenever for this particular input combinations, it's not going to work. The function is going to be 0 whenever Z is going to be 1. If Z is going to be 1, enable is going to be disabled, so the multiplexer is not going to do its function, so F is going to be 0. Whenever Z is equals to 0, it's going to be enabled. At that time, this is 0, this is 0, this is 0, this is only the 1. So F is equals to XY Z bar is its output. That is option A is correct. The number of two input NAND gates required to implement the above function, that is X, Y, XYZ bar is equals to this is implemented X, Y, Z. So it requires 5 NAND gates to construct this function. This is XYZ bar, so option C is correct.